Dr. Ryan Looper, welcome to CancerVac CEO Chats. Thank you for joining me today.
Thanks for the invitation.
You bet. Ryan and I have a long background together and have worked together quite a bit. And I have an enormous amount of respect, Ryan, for you. And just by way of, I'll give a quick little background, and I'm sure you can fill in the gaps and do a much better job at talking about yourself than I can. But yeah, it started for you with a degree in chemistry from Western Washington University, I believe, right?
Correct.
Then a PhD in organic chemistry from Colorado State University, which is a cool place.
Go Rams.
Yeah, that's right. And then you were a postdoc fellow at Harvard University studying chemical biology, which is pretty cool. Now you're a tenured professor at the University of Utah and serve as the John Huntsman Presidential Chair with the Huntsman Cancer Institute. Even though I see gray in your beard, and I can say that because there's a lot of gray in my beard.
I was just thinking the same thing. You're making me sound old.
You're a young fellow. You've accomplished a lot in a short period of time, and that's pretty impressive. Can you, I'd love for you to just, if there are any gaps on how you got to where it started to here and how you were able to leverage your background to participate, not just at the upper echelons of academia, but also in the biotech space as well.
Yeah, no, thanks for the introduction and the senior discount I guess I'm going to get. No, yeah, so I think something important to mention too, because I've been dealing with a lot of undergraduate students recently in this regard is, I came into college not knowing what I wanted to do, and I found organic chemistry by accident and absolutely fell in love with it. And I think that passion for what you're doing ultimately is what you need to excel and move forward. So I always love to give undergraduates an opportunity to find their passion, whether it be in my lab or another person's lab, because I think that more than anything is going to shape kind of where you go with your career. And so for me, that passion ultimately of thinking about small molecule chemistry and biology and therapeutics and helping people, that was the guiding force that got me to where I am today. And I think through my education, it was just one step at a time, learning the tools to do what we need to do. And then fortunately, I've had a chunk of time now in my career to actually dig into a project long enough that we can see the fruition of it actually being able to help people, which is just fantastic.
I mean, that's sort of the ultimate goal, right? I mean,
Yeah.
As a professor, you're helping kids in one way.
Correct.
My wife's a teacher. I understand that, but making a new drug, holy cow, that's good stuff.
I'll put that on the checklist from when I was an undergraduate and started in the lab and dreaming about if one day I could make a molecule that helps somebody, that would be amazing. So
one of the things that's impressive to me about what you've done is you figured out how to sort of manage and bridge this gap or balance, if you will, teaching, but also as a researcher in the biotech space. And maybe tell me how you did that. But also, I think perhaps a lot of our audience won't really understand what a researcher is and what that means. Because there's a lot that goes into that.
Yeah. So, well, thank you for saying I have it figured out. I don't necessarily know if I have it figured out, but I try every day. And when we think about, it's interesting because you do what you need to do to get it done is the mantra that always comes with kind of wearing all of these hats, right? So as an academic researcher, I'm not only teaching and lecturing undergraduate students, I'm helping them teach in the lab. I'm helping graduate students that are earning their PhDs do research on new research problems, and I'm teaching them how to approach science. And then, yes, then if you step out into the industrial world and are now thinking about more traditional employees and coworkers that you're working with, there are a lot of different hats that you have to wear. And I think, the beauty of it is that all of these whether it be academics or industry, they kind of have their ebbs and flows, right? So, in an academic lab, there's grant season, which gets really, really crazy. In a biotech, there's, oh, we're out of money season. And I think
every season for a biotech.
yeah, exactly. I think you run along just hoping that they're ebbing and flowing at different times. So you can keep all the balls in the air. But I think the biggest lesson I've learned is don't punish yourself too hard if you drop some balls here and there, because it is a lot to manage. It's a lot of work. And the way I see it is all of that effort is for a greater good. And so if you do happen to drop a ball every once in a while, be kind to yourself.
That's great advice, I think. As I've looked at your career, Ryan, you've spent some time researching in the space of oncology, also a lot of time in the space of anti-infectives. Do you have a preference or are there other therapeutic areas that you're interested in looking at and researching?
Yeah, so great question. So I'm a chemist at heart, and we often say that chemistry is the central science.
Yeah.
We have T-shirts, I think, when we get our degrees that say that. But in a sense, the chemistry has always been my focus. In the disease area or the biology where those molecules end up taking me, I've just kind of gone with it. Now that I've gotten into those disease areas and that biology, the disease biology enough, I do have a favorite. And I have to say it's infectious disease. For bad reasons. Well, not bad, for good reasons, but it's an incredibly tough space, and I'm sure we'll talk about that a little more in a minute. But I'm also working on a new glaucoma drug, so targeting ion channels. So there are lots of targets that chemists can go after. So our biology space can be pretty broad if we're focused on the chemistry.
I'll bet. It's interesting. I would imagine, I know this firsthand, and I know you do, but it'd be interesting to hear your perspective. Just this is hard work. It's long, it's slow, and it really is a slog. But it's important, right? Someone has to do it.
Correct.
And so what is it that motivates you to keep pushing through? More on the drug development side. I mean, I understand the teaching side a little bit more. That's a little bit more intuitive, but pushing a boulder up the hill every day, that gets tiring.
It does. And my students always laugh at me because if I'm not in the lab, I'm probably putting up drywall or something. Because that gives me an alternative where, I can put up a piece of drywall and finish it. And within a couple hours, I see some results. And that's something that doesn't happen in the scientific enterprise. And I think, when we think about answering big scientific questions, it's years of research until you start seeing the forest through the trees type of thing. And, I think the only thing that keeps you going is that innate curiosity and passion for what you're doing. And that's why I say, I think you have to have that to really be successful and get through graduate school and get through a pre-tenure assistant professor position and so on and so forth. But that innate curiosity is always there, and that's what drives me.
No, that's cool.
I mean, what nature does with some of these molecules is like the coolest thing ever. So it really is fun to uncover the mysteries of Mother Earth.
Well, and it's interesting that you say that because, and this is, so many of the molecules, especially in the anti-infective space, they really come from Mother Earth, right? These are natural organisms that we discover that can do some pretty cool things. And then people like you need to come in and figure out either how to replicate that, but usually it's converting it to a synthetic process, right?
Correct.
That's not easy.
No. And so, it's really cool that nature's given us this this essentially an invention wheel. So they started the process, right? So if I think about the anti-infective space and I think about antibiotics, we're talking about bacteria that have evolved for millions of years to fight other bacteria, and they use antibiotics as a way to ensure their survival. And so we can discover those molecules and we can understand how they work. And sometimes how they work is just so clever you can't stand it. It's like, I couldn't have thought of that if I tried. And then, at the end of the day, you're presented with this molecule that's incredibly structurally complex. It's incredibly hard to make for a human in the laboratory, and often it doesn't have all the properties that it evolved for, right? So it evolved in the soil to kill another bacteria. It did not evolve to kill, a cancer cell in my lung or a bacteria in a urinary tract infection. And so we, as chemists, get to redesign this molecule and move atoms around so that the molecule ends up having all the properties that we need it to have, which is fun.
That is really cool. I mean, Alexander Fleming really stumbled into that in the late 20s, right, with penicillin.
Correct.
But that, I think that leads us into a really good segue into the next point. Is what you mentioned earlier. You're a chemist at heart, and you really love the chemistry side of things. And now, as you start looking and through experience and such, this biological world that meshes with it. You see opportunities, right? And so what goes into creating a molecule as you discover this potential opportunity? How does that work? What's the process like?
Yeah, so it's a long process, as you alluded to earlier. But discovering a molecule and then understanding its biology or what it does, its intended use. Understanding that biology down to kind of atomic precision where you can now think about redesigning this molecule at the kind of atomic resolution to inhibit or do its biology at atomic resolution. It takes a long time to figure out exactly what that molecule is doing and what it needs to do. And so I'd say that's a really long part of the discovery process that takes, teams of academic scientists with different expertises a long time to really figure out. And then we as chemists really do think about, in the case of natural products or antibiotics, it's nature has given us this clue, but how do we move atoms around or change this molecule so that we can synthesize it, first of all, so that we can potentially synthesize it on scale so it could actually be a medicine, so that it has improved properties such as solubility or lack of toxicity. And so I think most of that process takes the experience and intuition of a chemist to really kind of understand what groups of atoms or functional groups might be good, might be bad, and how we might put those together ultimately to have a drug type molecule.
Yeah, it's interesting. Like you talk about natural products and then sort of manipulating that into a synthetic process. There are sometimes I would imagine where some of the parts of those natural products just they're not easy to replicate, or you have to have a portion of the natural product, and if nature stops making it,
correct,
you might be in trouble, right?
Absolutely. And so in my academic lab, we're working on a couple natural products right now. One of them is a really fun story that I won't belabor you with, but it's a natural product isolated from the Panamanian golden frog, which is now critically endangered. So you can't get the molecule anymore. And this molecule is so complex. I would imagine by now there are, 25 to 30 chemist years that have been put towards synthesizing this molecule, and we still don't have it replicated in hand. So a lot of time these projects will become, an academic or a graduate student research exercise, figuring out how to make this complicated molecule so that you understand the chemistry well enough that you can make a new molecule that's streamlined enough so that it makes commercial sense to think about developing it as a drug.
That's super interesting. And I like that analogy. I think it's a great story, because the next question I had for you is, as we mentioned earlier, you've figured out a way to bridge this gap between living a bit in the biotech space as an innovator and a scientist there, but also in the academic space. Why is it important? And do you think it's important for there to be some sort of a synergy or a marriage or a relationship partnership with academia and the biotech space?
I think absolutely there is, because well, we'll get the antibiotics has a very clear reason. We'll get to that in a minute. But I think in general, innovation, which is often driven at academic institutions. I mean, it's driven in the industry space, of course, as well. But speaking as an academic, our academic innovations, right? We often believe in them. We often understand their scientific value, but we're so under-resourced that we don't always have the ability to prove the potential of these things, and especially not in a speedy way like industry would do. And so I think, the ability to engage industry, develop collaborations, and help advance the science and raise resources that are outside the purview of kind of the federal funding system is absolutely essential to translating academic discovery ultimately to help people or help patients, if we're talking about the biotechnology space. And so that's critical. And I think it becomes even more critical when you're in a place like the University of Utah or Salt Lake City, where it's not necessarily recognized yet as one of the hubs of the biopharmaceutical arena. And so
it's coming along, though.
Oh, it's coming along great. And I think, I can tell by the license plates in the parking lots at the ski resorts that everybody's moving here, and we're going to be silicon slopes and silicon or biotech slopes here in the near future. But, as you're in parts of the country, if I think about, say the University of Michigan, or somewhere like that also has, amazing world-class university academic research going on, but probably not the local entrepreneurial or investment thesis that San Francisco and Boston have. I think, allowing a PI or a researcher to bridge the academic and industry space and push this technology as far out from the university as you can is incredibly important. Right. I know, for example, the project that we worked on together, if that was a project that was originally spawned in industry, that would have been killed 6 months into it, because we couldn't figure out what was going on or why these things were working, or so on and so forth. And so I think the ability to have those academic industrial partnerships to address the hard scientific questions that take a little more time without the pressure of the investment world is really critical for early stage discoveries.
Yeah, and I agree completely. I loved that experience and what you're doing right now. And I think it's amazing. And I think we ought to. I mean, I've always looked at the biotech industry really as kind of a poorly funded business development R&D arm of, well, not BD, but more R&D arm for big pharma, right? Let these guys take all the risk and figure out how to get it in the red zone, if you will.
Yes.
And then thank you very much, guys, for your 10 years of work. We'll take it from here.
Correct.
Right. So I think what you guys are doing is really amazing. We're at the company I'm with now, CancerVax. We're doing a similar thing with UCLA. And but on that note, there is kind of an interesting, I think, overlap between cancer and antibiotics. I think most people don't realize that as you set into some of these more aggressive cancer treatments, you're very, very prone to infection. And it's these bacteria that we're really worried about. And that's really been your life's work for the past decade or so, is these bacteria who mutate. There just are not good drugs to combat that. And that doesn't just affect someone who gets a MRSA infection or a urinary tract infection. That affects chemo patients and patients of all walks, people who've just had hip surgery or whatever the case might be.
Yeah, absolutely. And I think so. Chemistry is the central science. I often say, antimicrobial resistance is going to be the central demic of the pandemic, because I think a very similar thing, in the sense that antimicrobial resistance and our lack of innovation in the antimicrobial space is going to lead to this cliff where we are in a pandemic and have no medicines for these bugs. And I think, like you say, it doesn't just infect people or affect people who have a urinary tract infection, people who have COVID. And we've seen this recently in the last tridemic, the number of people that have actually died because of secondary pneumonial infections and not the actual viral infections is skyrocketing. And anytime you're in a hospital setting for chemotherapy, for a respirator for viral pneumonia, or any related healthcare setting, that risk of contracting antimicrobial resistance and infections is significantly higher. And so, this isn't just impacting, the infection space. It will affect all aspects of healthcare.
I agree. Well, this has been exciting, Ryan. What is what are some of are there any new exciting things you're working on right now that just get you pretty pumped up and excited?
Yes, of course.
What are some of your favorites?
Unfortunately, it's still in the antimicrobial space, but from a development perspective, right? So I think what I've really fallen in love with, and you've accompanied me on this journey for a good part of it, is so you've mentioned that I sit in the academic and the biotech space, but I think the third leg of the policy space is equally important and equally fascinating from a scientific perspective about, right. If we think about antibiotics, it's I have a drug that I never want to prescribe because I want to save it for the most drug resistant infections that we have. And then how do I go tell somebody that, we're going to make a lot of money and get investment for a drug that we're never going to sell? Right. It's just, but we know from a societal and humanitarian standpoint that these medicines are 100% critical. Yeah. And so I think, I'm fortunate because I bridge both sides. I also have the fundamental luxury of having a teaching appointment, and I'm not going to starve if things don't go well. But trying to think about how to tackle this incredibly complex politico-economic as well as scientific arena is really just fascinating. And I think, we've often mentioned the term guerrilla warfare as scientists trying to figure out how to get these drugs to market, despite and in spite of government and market forces is kind of fun in and of itself. But back to the scientific side real quick.
Yeah, go ahead.
No,
I think that's really cool. I know you've got, we could riff forever on this kind of stuff. It's really fun. And the world needs more big thinkers like you. And one of the things I've always really appreciated, Ryan, about you is you're one of the smartest guys I know. You're a unique breed in the sense that most of the scientists that I've come across and worked with are brilliant and smart, but you get them into a setting outside of science and they don't thrive. They don't do so well. And that's another area that you've been able to bridge gaps. You're quite unique and articulate and talented there. But I love that you're a big thinker. And like on that societal and political thing, there's a bill before Congress now, the Pasteur Act, that would do a world of good
Correct.
help the antibiotic space. And, not to just toot your horn, but let me try just a minute, because the project that you're working on right now is not just a new antibiotic, it's a new class of antibiotics. And most people don't understand that, but in my opinion and in my understanding, that's akin to a new penicillin, right?
Oh, absolutely. If we look back in history, I mean, you could debate the count, but the new classes, new mechanisms of antibiotics to enter the clinic, that's only been done like 14 times. And that hasn't been done in over 60 years for our most problematic kind of infections, right? And so going back to our previous argument and getting a little more personal for a second, we have a candidate. We have 5 kilograms of a drug candidate that would be the first new class of antibiotics for gram-negative bacteria to go in the clinic, and we can't raise the funds to progress that medicine because the market is so broken. And so when I talk about guerrilla warfare, about how do we get this into the clinic, we're stealing a penny from Peter and the NIH and trying to help this study, and we're trying to get $10 over here and so on and so forth, and that's challenging and frustrating, but that's I guess the challenge I accepted, and we'll get it done.
You will get it done. I have all the confidence in the world in you guys, and kudos to you. And we've done a segment already about the importance of intellectual property, which you understand and can talk about. And we're doing another segment coming up on, and you've alluded to this a little bit, is NIH and other things, but grant writing and the importance of there are a lot of federal funds that can really facilitate. It's not the same as an infusion of capital from a venture firm or something like that. But
correct, they're very different types of money.
Yeah, but
you can get there.
Yeah. Well, Ryan, thank you for your time today. It's been great to see you again, and I appreciate
absolutely.
You
it's been too long. We should have chats like this more often.
We definitely should. We just won't record the next one.
Deal.
Right. Thanks, Ryan.
Hey, thanks, Ryan. Appreciate it. Bye-bye.